Hello everybody. Let us start our discussion today. We'll see another experimental observation which was done and explained by Arthur Compton. The explanation came in 1923. And to explain this effect which we are going to discuss today, Compton evoked Einstein's idea of light quantum hypothesis. So this effect is called Compton scattering or Compton effect, and that's what we will learn today. Before we go into the explanation of the Compton scattering, the Compton scattering is, let me write what it is first. It is elastic and inelastic. Inelastic part is the one which is more interesting. Scattering of X-rays. Okay. So now, what is the meaning of elastic and inelastic scattering? Elastic scattering means wavelength of the radiation doesn't change. Scattering is like something is colliding with something. So X-ray will be colliding with electrons. So this is scattering of X-rays and electrons. For the elastic part, the wavelength of the X-ray will not change after the collision. Inelastic part, wavelength will change. Now, as you can see, this is the wavelength change or not is being measured in this particular experiment. So we need to have a way of measuring the wavelengths in the X-ray regime. The wavelengths of X-ray regime is of the order of angstrom or even lesser. Okay, so we need to measure wavelengths of the order of angstrom. Now, how do I measure wavelengths in the order of angstrom? In optical cases, you know that if I use a prism, it will break the radiation into its different wavelengths. So I will see from white light, I will see light of different colors. There are other things called gratings and all. And you have heard a little bit about the diffractions, and we have talked about interference of light in between the Michelson two mirrors. All these are experiments sensitive to the wavelength of the light. But it turns out that for all these experiments to happen, the diffraction or interference to happen, the path difference, if you remember, created between the two light rays or the two light waves has to be of the order of the wavelength of the light. And that requirement comes from a very little bit more advanced topic called the spatial coherence of the light, which we will not be able to discuss in this course. But take it for granted that you need the scatterer or the things which is responsible for the diffraction or interference, the path difference. So for interference to be seen, and you remember the diffraction is also a type of interference. This has to be of the order of the wavelength of the light, wavelength of the wave of which you are trying to see the interference or diffraction. Now it tells you that for this, Optical, I need of the order of 1000 or 5000 angstrom size objects or things that can create a path difference of the order of 5000 angstrom. In case of X-ray, I need something that create a path difference of 1 angstrom. So how can I make the interference or diffraction of X-ray possible, and how can I use that to measure the wavelength of a given X-ray? So we need to know that before this experiment can happen. So you need to revise a X-ray spectrometer if you wish. So let us first learn how to make an X-ray spectrometer. Okay, it turns out to make an X-ray spectrometer, what one can use is a crystal, a metallic crystal. So what is a metal crystal? So when I talk about a metal, it is not that the atoms of the metal are completely randomly distributed. Rather, they are distributed in a very nice, orderly manner. Like they will have constant distance if I consider one layer. So when I'm drawing this, so remember that the metal is a three-dimensional object. I'm just drawing a cross section over here. Okay. And they can be distributed many different ways. I'm just drawing one cartoon of it. So these are atoms, and there are many in the left and right. So that is one layer, if you wish. So one layer which is going through like this. If I draw the next layer, so the atoms can be, I mean, it can be just below that, or it can be like this also. Depends on what is the metallic structure. And then again, there will be another line, etc. It turns out that the distance between these are of the order of angstrom or even less, so that we can use these as to diffract or interfere X-rays. In fact, what happens is these layers behave almost like this is one layer or one plane in the metal, and this is another plane in the metal. So X-ray will actually fall when if you make the X-ray fall from one direction like this, it will see the first plane like this and the second plane like this. Remember, in Michelson interferometer, we are thinking about that there are two planes which are kept like this, two mirrors which are kept like this, and we are talking about the extra. So light falls in from here, it gets reflected from the upper surface, but it also, part of the light also comes in and gets reflected from the lower surface, and that extra path difference is what we are using. Here also we can do the same thing. One difference between Michelson's mirrors and here is that here I consider the planes are parallel to each other, they're not at any angle. So these are the first two planes in the metal. And it so happens that in principle it can go to, there are many other planes behind this also, it can go to other planes, but the reflection from the successive planes are minimal, so we don't need to consider them that much. So we have this metal crystal planes, okay, and they are at a distance a d, or let's call this a, let's call this distance a instead of d. There's no specific reason for that, it's just usually you'll see it's called a, so I just call it a. And now say the wave is the wavefronts of the wave which is falling to this are like this. So it's a plane wave falling into it. So I can draw like rays falling from this direction, and it will get reflected and it will go off that way. Okay, so it will get reflected from the top surface, it will also get reflected from the bottom surface. The question you are asking is how much extra path does the wave reflected from the bottom surface travel? And then again, so if I know the path difference, I can calculate the phase difference, and I can say that where I will see a constructive interference, where I will see a destructive interference. So that is what we want to calculate now, how much extra path it will travel. So for that, let me draw these layers once again. So these are my layers. Distance between them, we said A. Okay. So now as the light falls into it, so this is getting reflected from the top plate, and say it's also getting reflected from the bottom plate. I'm sorry, calling plate the bottom layer. And you see, as we know, so for the light, if we consider the wave fonts which are equal phase surface, so this is a plane wave falling into it. So those plane waves are like this, right? And what is this? So here, phase of light is same. So the phase of the light is same here and same here. Now you see that the extra phase that the bottom ray will show, see, is this much while getting reflected, and after reflection, again, these are my waveforms. So this much will be after reflection. So I can immediately write down just from the geometry extra path or the path difference is, see, up to this line the path is same from the top and the bottom reflection, and here also again the path is same between the top and the bottom reflection. So if I consider this point to this point in the top reflection and this point to this point in the bottom reflection, they have extra path here, say d1, here d2, and from the geometry it is clear that d1 is equals to d2. And if I consider this angle, which is called the grazing angle, to be phi, then if this angle is phi, you see this is 90 degree, this is also 90 degree, so this angle will be phi. So d1 is nothing but a sine theta, sine phi, so is d2. So the extra path is 2a sine phi. So interference maxima when does the interference maxima happens? Remember, path difference integral multiple of wavelength. So condition for interference to a sine phi equals n lambda. Okay, so this I guess that we have discussed in term while doing the Michelson's interferometer also. So here it comes in a different form where I don't have any angle between the two reflecting planes, but there is a grazing angle of incidence. Psi has a name, so psi is called grazing angle. Now that is all right. What happens if I make psi equals to 0? So sin psi is 0. So I get in the right hand side I get that corresponds to n equals to 0. So it means n equals to 0 means psi equals to 0. Okay. N equals to 1 means 2a sin psi is lambda, right, etc. Now it so happens if I increase the orders, so higher order means higher n, intensity of the peaks or intensity of maxima reduces. This happens because of something called diffraction, which you will learn in the next semester. So I will not go into much detail of it, but this is, you can take for granted that n equals to 0 is psi equals to 0 and n equals to 1 will give you 2a sin psi equals lambda. Now, how can I use this to make a spectrometer? I do the following. I have my X-rays, so I said that we are making a spectrometer for X-ray. Coming this way, so I have an arrangement where I have this crystal. Okay. And then I have a detector here. This angle, remember, we call psi. So what happens? So this X-ray is coming with a wavelength lambda. Now if you look at n equals to 0, that means psi equals to 0. That means that the maxima will happen along the direction of the incoming ray. So this is essentially no reflection. This will just happen in the direction of the incoming ray. But for n equals to 1, now what I can do is I can rotate this crystal. As I rotate this crystal, psi changes and I measure the intensity. So I plot psi versus intensity. And you will see that this expression is telling you there will be a maxima at the psi which is given by psi maxima will be sine inverse lambda by 2a. So there is a psi max here where I will see a peak. And I can put that, so what I can do, I don't know what is lambda of the X-ray. So I have this detector, which X-ray detector obviously. X-ray is reflecting off this crystal, and I rotate this crystal, change psi, and measure the intensity at different position of psi. That gives me this curve, and then I figure out at which psi I get the maximum intensity. I put that in this formula, and that gives me what is the lambda if I know A. So if we know A, so lambda is 2a sin psi max. So that makes an X-ray X-ray spectroscope, because I can now measure what is the spectral content of the radiation, which frequency the radiation is maximum. Okay. So now this means, what can I do now with this spectroscope, or what Compton did with this spectrometer? What he did is the following, that he made this X-ray scatter of some target and measure its wavelength. So first he will measure the wavelength of the X-ray directly, and then he will not the crystal, the spectrometer target, but some other target he will use to measure the wavelength of. He will use to get it scattered off that, and then measure the wavelength of that scattered X-ray. Okay, so for that he used a setup, and then first let us discuss the setup, so then it will be clear what he is measuring, and then we'll see that what was his observation. Okay, so Compton setup. First he has an X-ray source. Now there are many things which produces X-ray, but there are X-rays produced just like we have electronic transitions which produce characteristic lines, like we have for hydrogen Lyman alpha, Lyman beta, Balmer alpha, etc. lines. Similarly, there are characteristic lines of metals of X-rays, which are like line emissions, which are not exactly like the emission by Bohr atom, but kind of similar, I will say, because they emit at a certain frequency, certain wavelength. Okay, so this is some X-ray source which is emitting at that wavelength, and then it is kept in a lead shield, and there is a small opening. So this is just because you want to make the X-ray to come out from one direction only. So this is X-ray. So he used two different types of sources. One is molybdenum, 0.708 angstrom. I said of the order of 1 angstrom. So this is the wavelength of the X-ray source. And the other is tungsten. This is even smaller, 0.2 angstrom wavelength of the source. Okay. So after that, you have a scatterer. This is the scattering is by the electrons in this. So this scatterer was what you call a graphite. The thing that makes the lead of your pencil. Okay, so now this is how the X-rays are going and falling into it. Now you have an arrangement. When you come to do the experiments, you will see a real spectrometer here, which is optical one, but the same spectrometer also has similar arrangement, where all the detector part you can move along like this. So you can keep it at an angle theta if you wish. Okay, so I'm keeping it at an angle theta, and as you can imagine, it will not, the scattered X-ray will not come only along theta, but will come in all other directions. So you need what is called collimator, means that it rejects, so it hides the detectors behind something which will reject all the X-rays going in other directions. And what I'm drawing is actually how an X-ray collimator will look in cross section. What these are lead plates kept one after another. So these actually are like discs with hole in it. Okay, and they are kept one after another in succession such that only from a given direction the light comes in, the X-ray comes in. Okay, and with this arm, so this entire thing is in one arm, as you can see. So this is can be moved with theta. With this arm here you place the spectrometer. So this is the crystal. So what he used is a calcite crystal. A is of the order of 4.98 angstrom. Okay, which you see is of the order of 1 angstrom. It's not much different than 1 angstrom. So this angle, remember, is psi, because that is the grazing angle that we talked about. And you will have a detector somewhere here. And again, psi can be changed, as we said before. So this is the detector. So this is your Compton setup. Okay. So what are the different things he can do? He can keep this entire arm, at different theta, and for each theta he can measure the spectra. So for each theta he can produce this curve essentially. Okay, and so Compton can measure psi at resolution of 5 degree. Okay, so you can change psi by 5 degree. Gives, now what is psi? Remember, psi is the grazing angle here. Psi is the grazing angle here, and if I change psi for different psi, I will see different intensity. From that, I will conclude what is the wavelength. The wavelength will be the psi at which the maximum intensity happens. So changing psi, you can change the changing psi, you can measure the wavelength. So if I have a resolution of 5 degree in measurement of psi, that gives a resolution in wavelength for this crystal, calcite crystal, 0.001 angstrom. Okay, try to figure this out, how to get the resolution in wavelength from the resolution of 5 degree in psi, and A of calcite is 4.98 angstrom. I will not tell you that right away. I request you to think about it. All right, so this is what he could do. So let me remind you again what he could do. So he could change theta. For each theta, he can essentially measure the wavelength. He can plot the intensity as a function of psi, which will let him measure the wavelength. So let's see what his observation was. Now, if I remove the scatterer, I can directly measure the wavelength, and that wavelength is what is written over here. Molybdenum 0.708 angstrom, tungsten 0.2 angstrom. Okay, so now Compton did observation for 4 angles. So theta equals 0 degree, which is the direct I was talking about, 45, 90 and 145. And let me draw what he saw for these 4 angles. Okay, so this is, first is 0 degree, this is 45 degree. I want to draw them at the same common x-axis such that the observation becomes apparent. Okay, x-axis is, what is our x-axis? Psi, right? So I'm drawing that spectrometer intensity versus psi plot and trying to figure out where is the intensity. So I is plotted in every case. Okay. So when theta equals to 0, what do you expect? So these are the values of theta, right? So let me level them properly. So theta equals to 0, you will see that given the wavelength of the incident radiation, so molybdenum or tungsten, you will see a peak at that wavelength. So this will look like this. Okay. So what was observed at theta equals to 45 degree? Theta equals to 45 degrees. So this is, let me draw a vertical line which corresponds to the wavelength of the incident radiation, right? Theta equals to 45 degree, this was observed. You see a peak there and then something else start to come up. When you go to theta equals to 90 degree, the separation of this increases and it looks like this. And at theta equals to 145 degree, you have two distinct peaks. So you see the separation between the, so that another peak coming up at 45 degree, the separation between them is increasing. And don't take the amplitudes very exactly. Obviously, I am drawing by hand and I am not looking at Compton's original curve, so they can be not completely right. But the idea is that with different angles, with different theta, there are two peaks appearing and their distance is changing with theta. Two peaks. So two peaks will correspond to two wavelengths, right? Each wavelength gives you one peak. So two peaks will correspond to two Xray wavelengths appear as theta increases, as theta is not equals to 0. So two peaks appear as theta greater than 0. Distance between the two peaks increases with theta. At least from 0 to 145 degree, that is, we see that is the case. Different, or I should say all theta has the peak of theta equals to 0. So this peak is always there. It may change, the intensity, relative intensity of the two peaks may change, but that peak is always there. And what else do you see? Difference between the, okay. So the other observation is, now this he did with two targets, right? So one is molybdenum, one is tungsten. So if I call this distance between the peaks as delta lambda, see, I'm not leveling the axis psi here because they will give two different psi max from which I will calculate two different lambdas. That is difference between them I am calling delta lambda. Okay, distance between or difference between the so delta lambda at any theta is independent so let us call this lambda 0 which is the original, the frequency of the scatterer. It's frequency of the X-ray. So not frequency, wavelengths of the X-ray. So this is lambda 0. So this is independent of lambda 0. So what do I mean? I mean that if I can plot though he did the experiment for this 4 theta only, but still with 4 theta also you can plot. What do I plot? I plot theta versus delta lambda. At theta equals to 0, it is 0, and it increases 145 degrees. So it increases like this. And this curve is independent of what is lambda 0. The difference between the two peaks at any theta is always same, whatever be the wavelength of the incident X-ray. Okay, so this is what is observed, and this could not be explained with the regular theory of electromagnetic radiation, the Maxwellian theory, because in Maxwell's theory you don't expect the wavelength to change. You expect the same wavelength X-ray to come out. Okay, so this was reported by Compton in one of his research paper, and the next research paper he came up with this solution of this. So we'll start discussing the solution today, and we'll continue it in the next lecture. So Compton's explanation. What he has to explain? He has to explain the fact that there is two wavelengths here. So what he has to explain is two wavelength observed after scattering. One of them is fine. So one of them is like Thomson scattering, where it's elastic scattering. So that is okay. So that light which is falling into the scatterer is getting reflected off, kind of reflected off or scattered off by the scatterer, and that is what you observe. So that is elastic. That is all right. But the second wavelength, where the wavelength of the light increases, which means the energy decreases. So energy of X-ray. Okay, so let me not say that the energy decreases here, that will come as the explanation. But we see an inelastic scattering because the wavelength that comes out is different. Okay, so these are the things that he has to explain. So what is the explanation? The explanation is the following. He said that I have this scatterer. This is graphite. The graphite has this nucleus core. See that when Compton is explaining, Bohr's theory has already come. So when I say nucleus core, it's not only the nucleus. So let me write nucleus plus electrons core. So the core. So there are nucleus and there are electrons going around it. But graphite also has these electrons which are kind of free. So they are not coming out of the graphite, but they are not also kind of bound to individual nucleus. Okay, so they are kind of roaming around. They're loosely bound. Okay, so the electrons which are bound, the electrons in the core cannot be moved. Okay, so the electrons in the core cannot be moved if X-ray scatter of it, it cannot give any energy. Okay, so there are, so when the X-ray is falling into it, so there are X-rays which is scattering of the core. Okay, so these are interacting or scattering of the core electrons, and these X-rays cannot give any energy to the electrons, because the electrons, why it cannot give energy to the electrons? Because to change the momentum of this electron, see, if I want to give some energy, we know, at least classical physics tells me that energy is equals to p square by 2m. So if I want to give it some kinetic energy time, I will also give some momentum, because to change, so I have to change the momentum of the electron. The momentum of these electrons, the entire graphite core momentum need to be changed. Okay, so it is like you have one bead in a big ball. So you have a ball made up of many beads, and there is one bead which is like kind of glued to the ball. If I want to move that small bead, I have to move the entire ball. So I will need, if I want to change that momentum of that, I need to impart a huge amount of force on it. That the X-rays doesn't have. So these, the X-rays which interact with the core electrons, so these suffers inelastic scattering. This is what was expected from the classical theory. So this part doesn't have much new thing. What is new is about the scattering with the electrons which are in, what I said, like kind of free in outside. There he used two of Einstein's 1905 physics. So Compton used both photoelectric effect, or let me write light quantum hypothesis, or photon hypothesis, and special relativity. I'm sorry, here I have done a blunder. So this should be elastic scattering, not inelastic. It's elastic because obviously the energy doesn't change. These two, photon hypothesis and special relativity, Compton used to explain the inelastic scattering. So now this is very interesting explanation. So let me grab all your attention here. These electrons are rather free. So these electrons I can change their momentum, because if I want to change their momentum, I don't need to change the momentum of the entire uh, graphite uh, thing which is there, but just that single electron. Okay. The free electron momenta can be changed rather easily. Okay, so this is how he is arguing the free electron momenta can be changed rather easily. Second thing is important. The X-ray is made of photons. So photons, remember what are they? They are packet of energy, not distributed in space, but it's the entire energy is there in small region in space. So they are like particles, right? They're like particles of light. So Compton is using light quantum hypothesis here. They have momentum now. Do you remember that special relativity told you that if a light has an energy E, it has a momentum E by C, and a light which has a frequency nu, light quantum hypothesis tells you that has a frequency, has a wavelength, has an energy h nu, so it will have a momentum h nu by c. So the X-ray photons will have a momentum h nu by c. Nice. So now these momentum, these can go to, or actually not the, so part of it, scattering is happening, part of this can go to electrons. What happens if part of the momentum goes to the electron? So momentum will change. So say this momentum, the photon momentum, so let's call this P. And it's changed to P prime. P prime is less than P. So let's see what is P prime. So now P prime, the only way it will be different is it will be h nu prime by c. Right? Now previously it was P, which is h nu by c. And definitely you can immediately say that nu prime by c is nothing but lambda. So it will change its wavelength from lambda prime to lambda. And you can see P is less than P prime, P less than P prime, which immediately tells you lambda and P are inversely proportional. So lambda prime will be greater than lambda. So you will see a second peak now at lambda prime, which is at a greater wavelength. That is this second peak that we see in these plots. Okay, this is the qualitative explanation by Compton. In the next discussion, what we will do is we will exactly work out using special relativity how much the shift that you will expect. Okay, so let me stop here because otherwise the video will become again very long. Let me stop here, and the next discussion we'll see how we can calculate this shift. So what is the shift? It's called Compton shift. Okay, thank you.